In Part 6 of Lecture 4, we discuss bottom-up parsing. Bottom-up parsing approaches syntactic analysis from the opposite direction. It examines each token to determine whether it is going to push it on the stack and advance to another state, or take some variables from the stack and replace them on the stack with a non-terminal, effectively creating a parse tree fragment. When all the fragments are assembled into one parse tree, we are finished. Bottom-up parsing is all about emulating the actions of a push-down automaton. We are creating the state machine in a program and using a stack to keep track of whatever we have already read. Since the whole process is deterministic, we can automate the process. And bottom-up parsing does not require a grammar that is predictive as in top-down parsing. We don't need the first character to tell us exactly how we are going to expand a non-terminal. A sentence is a string of terminals that we derive starting from one non-terminal. If our string still has some non-terminals in it, it's not a sentence but a sentential form. It has the form of a sentence, but it just isn't a sentence yet. Because the sentential forms that we are interested in are in context-free grammars, they are on the right-hand side of a production, and we will call them right sentential forms. In bottom-up parsing, we will derive them from the rightmost derivation. Look at it more formally. If S ultimately derives beta, beta is a right sentential form for S. There are two main operations in a bottom-up parser, shifting and reducing. It is for this reason that they are called shift-reduce parsers. Shifting means moving the next input token onto the stack together with the next state. These are pushed together on the stack. Reducing means popping all the variables from the stack that comprise the right sentential form for a given non-terminal, and then replacing it on the stack with that non-terminal and the appropriate state. While shifting involves pushing on the stack, and reducing involves popping from the stack, shifting and reducing are not synonymous with pushing and popping. Shifting also involves advancing the input token stream and recognizing a change of states. Reducing involves a push after all those pops. The grammars of programming languages are context-free, and for that reason they can be processed by push-down automata. Since they are deterministic, we can emulate them on a computer, and it becomes important that we have the correct states and the correct transitions between states. This can be done automatically in a program called a Parser Generator. There are several commonly used when designing a language processor. The best known is YAC, which is available on Unix systems. The name is short for Yet Another Compiler. The Parser generator that is found on Linux systems is called Bison. While YAC is named for a Tibetan buffalo, Bison is named for its American cousin. Bottom-up grammars are called LRK grammars. The L indicates left-to-right scanning, the same as in top-down parsing. The R is for its generating a right-derived tree, and the K is for K look-ahead characters. There should be no need for any value of K greater than 1. We will take a quick look at an LR0 grammar. The big difference between top-down and bottom-up parsing is that we parse top-down, attempting to use foresight, trying to see what we are going to have. Bottom-up parsing is about hindsight, seeing what we have collected and what it gives us. So while an LR0 grammar, a bottom-up grammar that uses no look-aheads, may seem illogical, it will work, even though the grammar is very limited. You will see this on the slide, where an expression is either an expression plus a term, or just a term. A term will be very different from before. Here it will derive plus t or minus t, or just a term. F derives an identifier or a constant. It's clear that in this kind of expression, our terms will be much more limited than they were before. We start with a special start symbol that represents the entire expression and includes the end of file marker at the end. After this, you will see the grammar as we specified it before, but with the alternative right sentential forms separated into different productions. The data from the state machine, the push-down automaton, is saved within the parse table. There is an action associated with each state. For state 0, the action is shift. The token is pushed onto the stack together with the state to which we will transition. We find this next state with the goTo function, and its value depends on the look-ahead token together with the state that we are currently in. We have something similar with states 1, 4, 5, and 8. The action for state 2 is reduce by production 3. E derives T. This requires us to pop a term from the stack and replace it with an expression. But we also use the state on top of the stack along with the non-terminal to be pushed to determine the state to be pushed together with the new non-terminal. We do something similar for states 3, 6, 7, 9, 10, and 11. State 12 is different. It is the acceptance state. Reaching it means that we were able to complete parsing, and what we parse is syntactically correct. The manner in which LR0 parsing works is summarized in terms of these three operations. Shifting means moving a token and state onto the stack. The token obviously comes from the scanner, and the state to which we jump comes from the goTo function for that particular token and the state that we are currently occupying. Reducing requires that we know which production by which we are reducing. It requires popping variables, some terminals and some non-terminals, from the stack together with a state. We will use the non-terminal from the right-hand side of the production and the state at the top of the stack to determine the state to which we are going to go. We will then push this new state and the non-terminal onto the stack. The last operation is one that we will perform only once when compiling a program. We will accept that the program is completely and correctly parsed and end execution of the parser. Let's start with the expression minus 27 plus x. We have 5 tokens, minus, constant, plus, x, and end of file. We start by placing end of file and state 0 on the stack. The action for state 0 is shift. We need to find the goTo of state 0 and our look ahead, in this case the minus, and find that the goTo is state 5. We push state 5 and the minus sign on the stack. Now the action for state 5 is also shift. We find the goTo for our new look ahead constant and state 5, and it is state 7, and we push both constant and state 7 on the stack. The action for state 7 is reduce by production 8, which is factor derives constant. We pop the constant and state 7 off the stack, replacing it with state 11, which is what we get for goTo of state 7 and factor. The action for state 11 is reduced by production 5. We pop both the F and the minus, and we replace it with T. The top state on the stack is now state 0, because everything that was above it was removed from the stack. The goTo of state 0 and T is state 2, and we push it on the stack together with T. The action for state 2 is reduce by production 3. E derives T. Popping T means popping state 1, So once again, we have state 0 on top of the stack. The go-to for state 0 and E is state 1. So we push state 1 and E on the stack. The action in state 1 is shift. So we find that the go-to of state 1 and our token, which is plus, is state 8. State 8 and the plus sign are pushed on the stack. The action for state 8 is shift. We find that the go-to for state 8 and identifier, our current look-ahead, is state 6. So state 6 and identifier are pushed on the stack. The action for state 6 is reduce by production 7. Factor derives identifier. We pop identifier and state 6. State 8 is currently on top of the stack, and the non-terminal on the left of the production is F. The go-to for state 8 and factor is state 3. So we push state 3 and factor on the stack. State 3's action is reduced by production 6. Term derives factor. We pop the factor and we find state 8 is again on top of the stack. The go-to for state 8 and term is state 10. We push state 10 and term on the stack. The action for state 10 is reduced by production 2. Expression derives expression plus term. We pop term, plus, and expression off the stack. The non-terminal on the left side of the production is E, and state 0 is on top of the stack. The go-to for state 0 and expression is state 1. We push state 1 and expression onto the stack. The action for state 1 is shift. We shift our current token, the end of file marker, onto the stack with the go-to of state 1 and end of file. We get state 12, the acceptance state. We have successfully parsed our expression.